Alright, let's work with the normal distribution here. You see in front of you a normal distribution curve with some vertical lines, and we are given here that the mean is 7.5 and the standard deviation is 0.75. So as you know, the mean always goes directly in the middle. So 7.5 is directly in the middle. The mean splits the normal curve into two symmetric halves. Now, to find one standard deviation on either side, when we move to the right, we add the standard deviation. So 7.5 plus 0.75 will give us 8.25. And when I move to the left, I'm going to subtract. So 7.5 minus 0.75 gives me 6.75. And we do the same thing to move two standard deviations out. So I'm going to add 0.75 to the right, I'm going to subtract 0.75 to the left. And let's go one more just for fun. And we're going to have 9.75 and 5.25. So we can talk about the different values here based off the percentages. Now, if you've watched the empirical rule video, you know that 34% lies in each of these big, because within one standard deviation of the mean, you have 68% of your data. Now, between two standard deviations, we have 95%. Well, 68 is already taken care of, so I have 13.5% in each of these spots. If we go another standard deviation out, within 3 we have 99.7% of our data. So this makes up just 2.35%, and it should make sense that these numbers are getting smaller because the area is getting smaller. And then the tail, as we call them on each side, is 0.1%, because the entire graph as a whole is 100%. And it's symmetric, right? It's got to be the same on each side. So these are the percents that we are going to use to answer some questions. So number 2, what is the range for the middle 68% of birth weights? Well, remember, 68% is one standard deviation on each side, 34 and 34. So we're going to go from 6.75 to 8.25. That means we would expect 68% of our births to be between 6.75 pounds and 8.25 pounds. What about the middle 95%? Well, now we're two standard deviations away, because 95% is two standard deviations, so I'm going from 6 pounds to 9 pounds. So we would expect 95% of our births of our new babies to be between 6 and 9 pounds. 99.7, well, that's 3 standard deviations. So here's the mean, 1, 2, 3, 1, 2, 3. So we would go from 5.25 to 9.75. We expect 99.7% of our birth weights to lie between 5 1/4 pounds and 9 3/4 pounds, right? 5.25 and 9.75. What's the probability a baby will weigh less than 9 pounds? Well, here's 9. Less is everything to the left. That's all of this. Now, you could add those together. 13.5, 34, 34, 13.5, 2.35, and 0.15. You can do that, and that's fine. And you will end up with 97.5%. But you also know that on this side, 2.35 plus 0.15 is 2.5%. We know that these two sides together, this side and this side, have to be 100% together. So if I want the blue side, I could take 100% minus the red side and get 97.5%, because together they have to add up. So either way, you get the same answer. And last question on this video, if 400 babies were used for the study, how many should weigh more than 9 pounds? Well, this is more than 9 pounds. That's 2.5%. But 2.5% doesn't answer my question. The question is how many. So we are thinking 2.5% of my babies, of the babies. Well, we know how many babies are there. In this case, 400. So 2.5% of 400. Change your percent to a decimal, 0.025, multiply by 400, and we would expect that to be 10. 10 babies out of 400 should weigh more than 4 pounds. And that is the first example for the normal distribution.